Thank you, Greg, and we'll hold questions and comments till after the conclusion of the session. For the last presentation today, I'm actually going to be your presenter, and I just wanted to, let me plug myself in first. That's probably the, excuse me? State my name, yes. If you didn't know by now, I'm David Kosson, yes. But what I wanted to talk about is the Cementitious Barriers Partnership. I know some of you have heard about it, and just to give a quick overview of it, because this was a program that was started about a year ago to try to look at the opportunities for improvements in the performance assessment of cementitious materials that are used either in waste disposal applications or in ongoing nuclear facilities. And there are a lot of people listed up here. Let me just explain a little bit. The partnership came together out of working together between the Department of Energy and the Nuclear Regulatory Commission, the National Institutes of Standards and Technology, Savannah River National Lab, Vanderbilt and CRESP, the Energy Research Center of the Netherlands, and SIMCO. Each group bringing together different expertise and different perspectives that they have from this, and trying to draw data, information, and address some of the problems that are out there as a 5-year program plan. And then an external advisory panel that would be organized through our CRESP external peer review organization that we have there. The project goal was to develop a reasonable set of tools to predict the structural, hydraulic, and chemical performance of cement barriers in nuclear applications over extended time frames. And when we said extended time frames, we're talking greater than 100 years for operating facilities and greater than 1,000 years for waste management, recognizing none of us will be around here to verify that. But in the meantime, what we really wanted to do is look at a next generation set of models to overcome some of the limitations that we've been hearing about over the past 2 days, to have a mechanistic and phenomenological basis, provide a foundation for parameter estimation and measurement so that the models can be used. And we heard Greg talk very clearly about the need for data and what you learn from data. To be able to be robust enough to deal with the various boundary conditions and initial conditions, different cement, grout, concrete formulations that are used, saturated versus unsaturated, the external chemistry that you see in soils or when you're in above ground formulations, rates of carbonation, things of that sort, and to deal with rigorous uncertainty characterization and quantification throughout this. The reasons why this was put together was there was a perception that the current PA approach may not adequately represent all of the risks, that there are cases where there may have been overestimation of risks or underestimation of risks because of some of the simplifications that need to be done, not because there are great people working on this, because there are, but because of the absence of information and more sophisticated models that hadn't evolved. So really where this goes into is waste form selection, contaminant loading, the disposal decisions, remediation, D&D evaluations, and even things that come forward now as we look at operating facilities. There are questions of service life extensions for operating nuclear facilities. There are questions of now dry cask storage. How long are those casks going to be valid? How long do we have confidence in that? So really for the service life extensions and design improvements for future facilities as we go through a next generation or nuclear renaissance or whatever the current terminology is for it. But as we look into the future, how can we do a better job learning from what we've learned in the past? So these are just some pretty pictures. We've seen them all over the past couple of days, so I'm going to go over that. One of the questions was how do you begin comparing what you've learned as you've gone through? Because there are so many cases out there, so many different types of comparisons. We thought it very important initially to establish some reference cases, that being some prototypical cases, not precisely the ones that are being applied, so it's not Savannah River's vault or Hanford's tank or the like, because we wanted to keep this out of the regulatory space. But we wanted to keep it focused as a technical discussion about where the improvements are, but to be able to show over time where the reductions in uncertainty occur and how to achieve that and how to quantify that as a consequence of the models. So we really have Three basic types of reference cases. One's a cementitious waste form in a concrete disposal vault with a cap. No surprise, we heard about those kinds of scenarios a few times over the past 2 days. A grouted high-level waste tank. I think there's going to be a few of those occurring sometime over the next decades. Spent fuel pool was a concern because of the hydraulic situation. Each of these has a different type of configuration where the concrete materials are exposed and a different set of concerns. For example, in a tank, a large concern, as Karthik mentioned earlier, is the corrosion of the steel in contact with the concrete, both the grout inside and the external material. Alternatively, in the waste format disposal vault, Greg just spoke a lot about those issues. Spent fuel pool, you've got a large hydraulic head on the material, so little cracks can make big differences, and you also often have a borated water internal to that, so you have different chemistry that may affect it. And there's been a suggestion that we also put into a dry cask storage type of scenario, which is important because of the atmospheric exposures that may be there. But with each of these, you have a scenario, but you also have to have reference materials. You have an infinite number of concrete formulations, of grout formulations. So also coming up with and defining a set of surrogate low activity waste, cementitious waste form, a reducing grout, a reinforced concrete that was historically used in the complex, and a reinforced concrete that represents what the future design would be. So there's a limited set of prototype materials that we can actually then formulate, cast, expose to different conditions, make all the hydraulic, the chemical, the material level characterizations that are necessary to demonstrate the utility of the models and provide a roadmap for the specific cases going down the road that people may actually be carrying out. And similarly, that the data would be close enough that the data derived from this project would provide good first order estimates for actual applications as needed. So let's see if I can get this. This is not behaving now. Do we just die with a pointer? Or? There we go. And what we were doing was taking an extension or enhancement of existing tools. SemHide 3D and TAMES is a program that looks at the microstructure property of materials, of cementitious materials, developed by NIST. And Stadium, as we heard from Greg before, looked at the structural durability of materials. Leach Access Orchestra, you heard earlier from Hans talking about the coupling of full geochemical speciation, reactive transport type modeling. And then GoldSim has been used in the PA framework, as we've heard from folks over the past 2 days, and as a good integrating tool for bringing pieces together. So this was kind of the toolbox that we're starting with, recognizing that none of these tools captured the full range, but they need to be brought together, improved, and to move forward to what we're trying to achieve. So what this meant was development of a coordinated experimental and computational program. The conceptual model improvements, define test methods and parameter measurements, and model validation going forward. Keep in mind, this is a good just flow diagram of what a PA is, and we've heard about that. We're not focusing on the full PA, and you need to understand that, but rather the area of intersection is the source term area, the engineered barriers, really the cementitious materials and their intersection and interaction with the very close environment, that near field, so then that could in turn be handed off to the other PA type calculations and models, which define the fluxes through the system, that also define the fate and transport and exposure scenarios that other folks are typically dealing with and are in place. So as you look at it, you can link prototype cases through a first level model abstraction as a 2D scenario, looking at cross sections and the like. And then as you go forward, they can be recognizing that the test conditions and the data, both the model parameterization data and the field validation data, are essential moving forward. And looking at ways of doing more of that validation, there's a follow-on meeting to this, is a working meeting of what field test beds may be over the next 2 days. And then looking at this as single layer, as 3-layer models, as you heard earlier, or how to deal with the abstractions for the next generation of models that Greg was just talking about, to integrate with the performance assessments. This, we've seen pictures as just as an abstraction. Recognizing that as we go through this, we have a combination of physical stresses on the system. We go from a microcrack material up through potentially through crack spalling, and we have coupled physical and chemical processes occurring throughout. One of the questions, I put this in today just because there was a question that David Esch brought up about the potential significance of event-driven processes. And this was a fairly simple comparison of a simple diffusion model where you averaged, where it was completely saturated. Then if you took the chemistry and added the chemistry onto it, and then what happens if you went to the coupling the chemistry with the event-driven rainfall or infiltration patterns? What might be the order of magnitude on that? So what you see here is this would be your release if you considered a semi-infinite material with a zero boundary condition, which is a first order approximation that's been used in some of the past PAs. And then here, this is what the actual would be if you just considered constantly saturated conditions, but now you put chemistry on top of it. And you see over here, this is for calcium, which in this case is a major constituent, and lead I just chose here because we had data and that it's a very pH dependent, so it has a lot of chemical interactions there. But then what happens if you start putting in the event-driven processes? That being, if you took each rainfall event, and what we did was we took a 20-year history of rainfall events at Savannah River, or Aiken as we picked, and Richland at the time, and cycled through that to see the impact of that. Because what happens is in between those infiltration events, during them you get infiltration, you get release, but in between then you get gradient relaxation within the material because of that intermittent nature. And what you see here is the difference between an event-driven and what was considered as a continuous release over here, and the difference when you start looking at those individual events. And what we see is when the chemistry gets more significant, the impact of that even becomes greater. So I think it just reinforces something that David said yesterday, is the need to be looking at event-driven processes, not just temporal averages at large scales. This is an overall integration of the processes and the phenomena that are being explored through this. And what is the scenario definition obviously is an input from the performance assessment or from your conceptualization of the system that you have, including the physical configuration, your external environmental interface, and the material properties. The whole durability and release comes through to a whole set of different types of processes that occur. And in turn, ultimately, some of these are important for some applications and some are more important for others. Some may be totally unimportant for particular applications. And then understanding which are important, where, how to rank them, and have some heuristics as you're doing going through the process to select from one to the other. So which of these do you really need to consider? You know, maybe carbonation, maybe chloride attack, and maybe the radiolysis may not be important at all in this case, and something else, maybe sulfate attack, may be important in another case. But some heuristics to be developed to drive this, to help people work through that. But then ultimately you're coming down to what is the chemical performance, which is really contaminant release and change in redox and pH gradients within it. And then the hydraulic performance, very important, whether we're going to have flow through the material at what rate and how that's going to evolve with time, and the structural performance. An example of this you saw with Sahini when she gave her talk earlier, where she picked a particular scenario and she was just looking at the sulfate attack, these pathways coupled in yellow right now, with all the feedback loops of the damage mechanics and how that feeds back into the acceleration of diffusion, for example. Now, an alternative pathway could be if you coupled it with the talk that Greg talked about earlier today and said, okay, let's do the feedback in terms of how it affects the percolation through the hydraulic properties with that very nice model that Greg put up just a few moments ago. And that could give you the feedback routes that it would give you in terms of the percolation with event-driven processes back to it. So flowing through this sort of program in different ways would allow you to look at these different scenarios in a much more robust formulation. Then one of the things, we've had 2 reports that are coming out there in publication right now being formatted and the like. One was dealing with a broad literature review of the different information that was available from the cementitious materials on each of those properties and phenomena that I had in that last slide. and that will be available on the website shortly. And the second was one that reviewed a whole bunch of different assessments that were going on domestically, performance assessments in the past, other types of environmental assessments, international data that was available, to say what really has been the modeling approaches that have been used, what have been the important assumptions that people have made, where are the uncertainties and the opportunities in all of this, how has uncertainty been approached in all of this, and then what are the major conclusions from that. And some examples of performance assessments that were looked at. I'm sure some of you recognize some of these. Some examples of other types of assessments that are under RCRA or under NEPA that were done, or NRC license termination rule, various things, because all of these include different types of assumptions and trying to understand the waterfront of where the opportunities lay for improvements and what people have been forced to do because of absence of information, or just because it was not necessary if it was good enough, and then it allowed for the decision to be made. So some of the key summary and key assumptions that were made is that for these types of facilities provide for low-level D&D and the like, there was a wide variety of the types of assumptions in terms of source and release transport pathways, whether or not credit was taken for in the source term or not, and whether or not the cementitious material served strictly as physical barriers or physical and chemical barriers, or whether they were ignored entirely and just said this is a barrier that's absent. We heard an example of the other case where a metal barrier was just considered not there when Eric spoke, I guess, earlier this morning in the beginning, how the canister was not needed to be considered or wasn't being considered. Well, in some cases, the cementitious barrier was not being considered. Related to release, there, as I said, from no to large credit for, a lot of times they're very gross simplifying assumptions for material performance because of the absence of information. The physical failure was also often represented as a change in bulk hydraulic conductivity. It was most often represented as instantaneous changes going from an uncracked state to a cracked state at some point in time. So therefore, the capability, there was not confidence in the capability yet of looking at the evolution of damage in the material and how that fed back into the hydraulic properties. So some of the things that you saw in today's session gives you a window into what may be possible going into the future to address that need. As a chemical barrier, usually it was in terms of a linear partition coefficient. There was typically in terms of reducing conditions and a mass balance approach for looking at the rate of progression, not taking into account necessarily the impact of gaps that are present during the material placement or the system design, or the initial cracking that may be there, or the exposure conditions leading up to the closure state. And then what we see also, we heard some of the discussion today, that going from a strictly KD approach to a solubility-based approach for some of these constituents is a transition being made right now in modeling and an opportunity going forward. I think Greg commented earlier the opportunities now of looking at more fully coupled chemical and physical processes that allow more robust analysis of these situations. Okay, so if you summarize what is the CBP going to do in relation to key knowledge gaps, one of the big questions that came up is what are the initial conditions from after a few months to years of the material waste forms with respect to physical integrity, cracking, gaps at interfaces, and chemical conditions. There is not as good an understanding as most people would like about what that initial condition is that you're modeling from. So in this case, looking at field data, field test beds potentially, characterization of core samples or other existing material will help address that issue to give us a better starting point. Also, what is the actual material properties? The Thames model that is being developed right now will be able to take a cement hydration process or a paste hydration process and in turn go through at a very micro scale modeling of that and give us out of that diffusional and hydraulic conductivity properties from that, as well as mineralogical properties, building on this earlier work from NIST. The testing of materials, beginning with the reference materials, is to give you the actual parameter estimates that you need to work with these models. What are the effects of the primary aging processes? And the big ones are primary constituent leaching, decalcification, for example, carbonation, we heard about oxidation, sulfate ingress and chloride ingress. How is that going to affect all these feedbacks in terms of the chemical and physical and hydraulic properties? And what are the issues of the coupling of these processes? Where are the feedback loops synergistic? Where are they antagonistic? Where do things get better as opposed to getting worse, which is possible also. If you have a precipitation and a pore structure that serves as a pore sealing mechanism, for example, that could be beneficial. So the approach to stadium and plant enhancements will look at the effects on the structural and hydraulic durability. The leach access orchestra is looking at the effects of the chemical properties and constituent release or leaching. And then Thames looking at how to look at the microscale and couple that back to these other models for changes in properties in response to change of the microstructure of the material. And then model integration with the coupling to the PA models. For example, pore flow is one that we heard about from Greg earlier, but allowing GoldSim to kind of bridge across that to couple with those scenarios. Another one is, what's the effects of event-driven processes that have high nonlinear responses? And David could have been a straight man for me yesterday on that one, because what you see is some of these things, for example, the Richards equation that Craig Benson was talking about earlier today is very highly nonlinear. And that nonlinearity does not bode well for averaging infiltration over an annual time scale, just as one example of event-driven processes. Other event-driven processes are shocks to the system, thermal shocks or external loads and seismic events, for example, that suddenly need to be looked at as an event-driven type process. So finally, what is the impact of simplifying assumptions such as saturated or constant unsaturated conditions? What's the sensitivity analyses to these different assumptions? So we know when is it safe to make these assumptions or to do the model abstractions that Greg was talking about for computational efficiency or for being able to bring closure in reasonable timeframes, and when do you want to avoid them? Because even at smaller time scales or more smaller spatial scales, looking at the coupling gives you insights as to when the simplifications are reasonable and when they're not. So the expected impact will be a set of computational tools that will be applicable for performance assessment and design, hopefully reducing the data gaps for relevant systems and helping the overall PA and design process. So that's just a quick overview of that. At this point, what we would like to do is go in